Well, today I would like to just do primarily review, but we do have an effort to try and finish the more important material of the semester. I need to look at some of the material from the next section, which is on Wednesday next week, in regards to arbitrary coordinate transformations. I'll make this kind of short on this one. But you need to have seen this. I don't want to skip over it. And it works like this. Suppose you have a general coordinate transformation. Like here's polar coordinates. This is if you think about it abstractly. If you think of a coordinate transformation between x, y coordinates to u, v coordinates in general, what if I wanted to transform a rectangle from u1 to u2 and v1 to v2 into a piece of a sector, that is a sector minus a sector, right? Piece of pizza minus a piece of pizza. I like that. You can do it with this coordinate transformation, right? X as a function of u equal to u cosine v, and y equal to u sine v. Really, u and v are r and theta, so you can think of it as r cosine theta and r sine theta. That's what u and v are. So I just call them these different letters. And that's what does it, actually, right? Because if u goes between two angles, u1 and u2 here, and v goes between two radii here, that's in xy space going up between these two rays and these two radii. And so you can make a coordinate transformation. And what we found when we made that coordinate transformation was that we had to rewrite our integral a little differently. We couldn't put dr d theta, we had to put r dr d theta. And that makes us think that maybe for more general coordinate transformations, we can do it from other coordinate systems that are more abstract, that have the right symmetry for a different kind of problem. So we'll say this, a map or function, map just means function, P from a plane region in UV space into XY space can be used to make some integrations easier, such as in polar coordinates. Let's look at this one here. This is the most popular type, is a linear transformation. We just have a number times u plus a number times v is x, and a number times u plus a number times v is y. We'll call that a linear transformation. If I write phi of uv equal this means what you have is this one is x and this one is y. So that's the idea of a coordinate transformation. That x equals this first component, y equals this second component. And if x is a number times u plus a number times v and y is also, we call it a linear transformation. And what happens is things like this. We'll put it on the next page. If I let, in this case, x equal u plus v and y equal u minus v, then the u-axis and p-axis become these new ones, right? If I, for instance, put v equals 0, v equals 0 means that I get x equal u and y equals u. I get this line right here. This is the line where v equals 0. That must be the u-axis. And if I put u equals 0, then I get v and minus v. So x equals v and y equals minus v. That's parametric equations for the line y equals minus x, right? If u is 0 in here, so I'm on the v-axis and uv space. Then I have x equals v and y equals minus v, right? But that's parametric equations for y equals minus x. It's this line. So this line is now the v-axis, u equals 0. Now what you see is these linear transformations, you start to realize, actually transform lines into lines. If you put in the u-axis, a line, you get out a line in xy space. This is xy space, and this is the u-axis and the v-axis. All we did was really turn these things 45 degrees to get the new coordinates. So each point in here, you can draw perpendiculars to get the uv coordinates, and then you can rotate this thing to get the xy coordinates. So there's a more interesting coordinate transformation. And without going into all the details, I don't want to do some exam review for the exam on it. Let me just say that this also carries over to higher dimensions. And Okay, what kind of page here? Indicate. Maybe I put them out of order. That's what it did. All right. Well, there it is. So we'll say a linear transformation is one like this that we said. And in general, we want AB minus BC not equal to 0. What happens if AB minus BC equals 0? It turns out it transforms the whole plane into a line, so it's not very interesting. You want to turn a plane into a plane, so you're just making a coordinate transformation, not reducing the dimension of your space. So it takes lines into lines, line segments to line segments, and in fact, it takes parallelograms to parallelograms. Parallel lines remain parallel under a linear transformation. So a couple of the problems with the homework is say, well, suppose we took this rectangle with interior 0 to 2 on the x-axis and 0 to 1 on the y-axis. And we do the coordinate transformation we just said. Let x equal u plus b, not this is x. And let y equal u minus b. And the idea is that this means, what you're saying when you say phi of u is the coordinate transformation, you mean x, y is equal to u plus b and u minus b respectively. And so all you have to do under a linear transformation to see where this rectangle moves is see where its corners move, right? Because then you can just sketch the line segment between them, knowing that line segments go to line segments. So what you do is you find, say, well, the corner 0, 0, if I take this map, d of 0, 0 is, let's see, 0 plus 0 and 0 minus 0, it still gives 0, 0. Here's another property of linear transformations that takes the origin to the origin. So we still, if we take this rectangle in UV space, then this point here maps to this point here. You take phi of this point, you get this point. And then if you take the point 0, 1, this corner of the rectangle, right? Then, well, let's see, 0, 1, I take 0 plus 1, and that's x, x is 1. 0 minus 1, y is minus 1, so it goes to this point here. So this point goes to this one. And then this point, let's see, 2, 1. 2 plus 1 is 3, 2 minus 1 is 1, goes to the point 3, 1. So this point here goes to the point here. And now, and then finally the last point will map to this one, 2, 2, if you just plug in 2, 1, you'll get 2, 2 out of this. And what you find once you take the image of these 4 points, that is what the function gives you for these 4 points, just draw the line segments between them because it takes the line segments between these, the line segments between these. And then if you have the interior of the rectangle here, you'll get the interior of the rectangle here also. So this rectangle is mapped by this linear transformation to this parallelogram over here. It takes parallelograms to parallelograms. It can be a rectangle again if it's special case, but it doesn't have to be. So there's how you find an image. You map the corner points when you have a linear transformation. You can say what point maps to 2, 4. Well, since x is u plus b and y is u minus b, you just want u plus b equals 2, and u minus b equals 4, and you're going to solve that for u and b. You have 2 equations. If I add these 2 equations, for instance, then the b's cancel, and I get 2u equals 6, adding those down, right? U plus u, 2u, and b's cancel, and 2 plus 4 is 6. That means u equals 3. Now I can plug it into either equation. 3 minus b equals 4, b must be minus 1. So I have the point 3 minus 1 as image 2, 4. So you can do nice things like that. Now, here's what you get for integration. Because it takes parallelogram to parallelogram, if you do that double integral in xy space, right? What happens when you try and transform it over to UV space? All those rectangle areas you're adding up become parallelogram areas. And they have a constant, they have a translation factor according to this thing here. I wish I had time to derive it, what is it called the Jacobian. Your book writes JAC. I think in the literature it's usually J, so I put J. But JAC in your book. Of phi, the coordinate transformation map, is defined to be, we give it this notation, dxy duv, it's like a generalization of the partial derivative, is this determinant of partial derivatives. So the Jacobian is determinant of partial derivatives. We put x and y in the first and second rows, and u and v in the first and second column. So it's dx du, dx dv, dy du, dy dv, determinant. That turns out to be the magnification factor between the parallelograms in uv space and the rectangles in xy space, which tells you something interesting. You can evaluate an integral in xy space by transforming it into uv space, multiplying the integrand by this, which is the scaling factor between the rectangles and the parallelograms. If we didn't prove that, I'll just wave my hands real fast and do a hand waving proof again. I hate doing that in math class. We'll finish this semester if we want. So we put the integrand in, but we have to multiply it by the scaling factor between the parallelograms in UV space and the rectangles in XY space, and then we'll get the same result. So we can integrate in UV space instead of XY space, which may take advantage of the symmetries we have, just by multiplying the integrand by the Jacobian. That's the big theorem. We define this Jacobian here. We call it the Jacobian of the coordinate transformation. Phi of uv equals x of uv, y of uv, some function of uv, some function of uv. It doesn't have to be a linear transformation even. It turns out it still works. Then it doesn't take rectangles to parallelograms. It takes it to something else. But this turns out this thing comes close enough up for nice coordinate transformations. If this determinant is 0, then it doesn't work because it's taking like rectangles to lines somewhere in there, and so, or points. And so it doesn't transform areas to areas. It takes somewhere in there, points to points. And you get singularities in there that you can't guarantee the mixed theorem. But if the Jacobian has one sign, it has to be continuous also in the theorem coming up. And so it's never equal to 0. Then this is the scaling factor, which will transform your integral in xy coordinates, z coordinates, and here's the major concept. If phi, a coordinate transformation mapping, is a C1, anybody know what C1 means? This is what you're supposed to pick up on this course. I'd be surprised if you knew, but I thought maybe you saw it last calculus 2 or something. It means it has one continuous derivative, at least. Might have more than one. It has a continuous derivative at least. Mapping this function. So if it's a function with all those partial derivatives having, all those things having one continuous derivative, from the interior of a region D0 in UV space into the interior D in XY space with one sign, plus or minus for the Jacobian, never equal to 0. And the integrand is also continuous, so that the integral exists. Then you can evaluate your double integral of f of xy dx dy in xy space as the double integral over the image, whatever the coordinate transformation, either like we showed you in polar coordinates, you can take a rectangle in UV space into a piece of a sector in XY space, right? So this might be a piece of a sector. A piece of a sector D taken from a rectangle in UV space. So if we're going from polar coordinates, we could integrate over a rectangle with constant endpoints. And then we can integrate over a piece of a sector in XY space. It'll be very easy because here we have constant endpoints. So transform from XY space with integral nasty to UV space where it's hopefully easier. And you can do that provided you can transform this integral into the easy polar coordinates or whatever coordinate transformation is by writing x and y as a function of u and v, your coordinate transformation variables, times the Jacobian integrated over u and v. Here's the fun thing. Guess in polar coordinates what this Jacobian is. Turns out to be r. I put it on the previous page, I think. Going back to the backwards. Maybe I'll just show you real quick. So note, if you take phi, the coordinate transformation of r and theta, go up big because I put people online. Sorry about that. So I take a coordinate transformation, x, y variable to r theta variables by saying x and y, let's see. Are equal to r cosine theta and r sine theta. That is, if this is x and this is y, and the coordinate transformation. What is the Jacobian of this coordinate transformation? Well, remember, we write it with this notation if you want. It's dxy dr theta. And it is the determinant of dx dr, dx d theta, dy dr, dy d theta. Well, what's dx dr, right? X is r cosine theta, so dx dr is cosine theta. What's dx d theta? If I take the root of r cosine theta, treating r as a constant, is r times minus sine theta. Then dy dr, y is r sine theta, treating theta as a constant, we just get sine theta. And dy d theta, the root of r sine theta with respect to theta is r cosine theta. And let's see what's that. Cosine times r cosine is r cosine squared theta minus this one times this one, minus r sine squared theta. It's equal to r times cosine squared plus sine squared. It's just r. That said, that's the proof that if you want to evaluate an integral in xy coordinates, f of xy, dx dy or dy dx, it doesn't matter, over some region d, you can rewrite it according to our thing we just did over region d0, that's the image. We sometimes write d equals phi of d0, d naught. So d0 is the reason in UV's case, this image is D, is the integral of f, and we'll replace x with r cosine theta, y with r sine theta, and then we have to take the area multiplier, which is the Jacobian, r times du dv, we said, which is now dr d theta. This is the Jacobian, this is the du dv. What that shows is that r factor is predicted by this coordinate transformation. So here's a second proof of we did the proof for one way. This is the proof for general coordinate transformations. If you apply it to polar coordinates, you show the Jacobian is r, and that's the formula that we did in another section. All right. Comments on that? I should add one more comment. If you look at the theorem, it's actually not the Jacobian that goes here, but the absolute value that's Jacobian. Don't let the braces here for the determinant mixed up here with the absolute value. This is sometimes the Jacobian comes out negative, and you need to multiply by the absolute value of the Jacobian. Minus the area here compared to the area here. So the theorem, wherever it went, there it is. You can see it, so I'm going to go through it. Says that it's f evaluated function of the new variable times the absolute value of the Jacobian. That's the theorem that's used. Where u is r and v is theta. That theorem So the coordinate transformation we previously had for polar coordinates first. And then we'll just mention that we can actually do this with functions of 3 variables. It comes out exactly the same. Under the same thing, that f has to be continuous, and you need a non-vanishing Jacobian with C1 functions you're taking partial derivatives of. Then it's the same thing. You replace you put the integrand in terms of x of UVW, y of UVW, z of UVW, 3 variables in a 3 variable transformation from 3 space to 3 space. Put the absolute value Jacobian here, where the Jacobian is actually a 3 by 3 determinant. Maybe I should write it out there. The Jacobian is now dx du, dx dv, dx dw, dy du, dy dv, dy dw, dz du, dz dv, and dz dw. A 3 by 3 determinant. It works just the same if you have similar restrictions. And actually, remember spherical coordinates. If you put in the spherical coordinate transformation, that x is rho cosine theta sine phi, y is r sine theta sine phi, and z is rho cosine phi. The Jacobian you come out with will be rho squared sine phi, showing for that you want to transform from x, y, z coordinates to rho theta phi coordinates. You need to stick in rho squared sine phi. And you can do this now for general coordinate transformation, 3 space, by putting in a 3-dimensional Jacobian there, absolute value. Okay, I'm going to leave that there and let you take a shot at the homework on that. I want to make sure we spend the rest of the time preparing for Monday's exam. I give you a bunch of practice problems. Is there anything in particular that you want to look at off of there? Anyway, this is the end. This is the crescendo of the chapter. It says now look at general coordinate transformations. Here is how we can do multiple integrals in pretty general coordinate systems. I can put this up on the help. Anything giving trouble? We've been trying some of these at home. 2E? All right. I expect most of the problems to be similar to these, but you'll be able to do homework or problems similar to anything in the homework. 2E, actually, this is a terrific problem because, look at the action, it's not my view to see. Yeah, this one is good. Okay, 2E. Sketch the region and evaluate it by changing the polar coordinates. I'm writing scribbly here, maybe it was. All right, Q scribbly won't get anything, right? All right. There's the integral from minus 3 to 3, minus 3 halves, 3. The integral from 0 to square root 9 minus x squared. X squared plus y squared dy dx. With experience, this, oops, I think, the document camera, there it is. Hopefully you were reading it off the board there, 2E. Sketch and evaluate this region. I intended to do a problem like this before. We just didn't have enough time. These 45-minute lectures are killing me. I already couldn't finish the source before. Now I'm just, anyway. What you do when you want to make coordinate transformations and you already have an integral in the one system, normally is you draw a picture of it. If you draw the picture, then you can see what the bounds are on the new one. That's the way to figure out what the new bounds are. Figuring out just from looking at these bounds is very difficult. So what you do is you first sketch it as it's suggested up here. If this has dy on the inside and dx on the outside, it's a vertically simple region, right? It goes between. This is the bottom curve. Y equals 0. And this is the top curve, y equals square root 9 minus x squared. And this is the minimum x. Could be a vertical line or it could degenerate to a point. And this is a maximum x. Right? So think of it that way, a vertically simple region. I'm going to go from minus 3/2 here to 3, twice the distance to the other side. And my top curve is square root 9 minus x squared. What does that look like? Y equals square root 9 minus x squared. Better question than you do it, but. Oh, awesome. Yeah, it's a circle. Square both sides to see it's y squared equals 9 minus x squared. This is another important point. The square root comes up a lot. Add x squared over and get x squared plus y squared equals 9, which you recognize as x squared plus y squared equals 3 squared, a circle of radius 3. So the top curve is this circle, goes up to 3 here. That means it also comes over to 3 right here, but not down all the way over here. And then the bottom curve is y equals 0. Here it is. So I go between a vertical line at minus 3/2, a vertical line at 3, which just degenerates to a point, below the arc of the circle, and above this bottom point. So take this region that you can figure out from this, min x to max x, bottom curve to top curve. If it's a horizontally simple region, if dy is in the outside, then you go min y to max y, left curve to right curve. Right? So it's very similar. But here's your region R. Now try and write that region in the new coordinate system. We'll say if we want to write this in polar coordinates, then we need to think of this as a simple polar region. Right? This is why I say it's screaming for polar coordinates. Look, I have an arc of a circle here. That's really easy in polar coordinates, right? And an arc an integrand, x squared plus y squared. Remember, that's equal to r squared in polar coordinates. So that simplifies too. So you can put in x equals r sine theta and x equals r cosine theta and simplify it if you like. But better to just recognize x squared plus y squared is r squared directly. dy dx now becomes r dr d theta. Coordinate transformation. R is your Jacobian. And then I just need to write the endpoints for this region in polar coordinates. And remember, in polar coordinates, what you want to do is think of it as going between what we call a radially symmetric region, between a fixed angle, theta equals one direction, and a fixed angle, theta equals another direction, an inside curve, which here is just the origin, and an outside curve, which here is just the arc of the circle. So that's what I'm going to think of when I do this. That doesn't look like a circle, does it? I guess this didn't work the axis quite the same scale. But, the idea is you're partitioning it up, and theta and r into these kind of little regions, and adding up all those little regions. And when you do that, what you're thinking of is the beginning rate is this one, so it must be theta equals 0, right? That's the 0 direction for angle standard position. So theta is going to start at 0, and then the theta max is this one. Uh-oh, that's a toughie, isn't it, right? The equation of the line is x equals minus 3/2. If that was the y-axis, it'd be easy to be pi over 2, right? In fact, that's not even, I'm sorry, I wrote it in the wrong spot. It's not so easy with that. Let's do it like this. I'm sorry. We're going to have to break this up into 2 pieces. That's why I think it's a harder problem than we thought. We're going to do this one here. I'm going to break this up into 2 integrals. Same integrand and same area element, r d theta. But I'm going to call this region 1 and this region 2. Down between this one here and this one here, and then between this one here and this one here for region 2. So the first integral is going to go from 0, whatever angle that is. What is it? Well, if this is minus 3/2 and this radius is 3, this is half as long as this. This must be a 30, 60, 90 triangle. This angle must be 2 pi over 3. Right? in this triangle, the base is half the hypotenuse. It's a 30, 60, 90 triangle, right? If you had a triangle 1/2 square root of 3, which is 1 for 30, 60, 90, it's just 3 times that triangle. So that's the angle there, and then this angle here is theta equals pi since it goes down to negative y-axis. So what I'm going to do is, on this first region 1 here, I'm going to integrate theta equals 0 to theta equals 2 pi over 3. From an inside curve, r equals 0, to an outside curve, r equals 3. All right? Inside curve, outside curve, because you're thinking of the radially symmetric region. Ray to ray, and inside curve to outside curve. But on the second region, I have a different outside curve. I'm going to integrate starting at theta equals 2 pi over 3. That's the beginning ray, and the ending ray is pi. And now, the inside curve is still r equals 0, the origin, but the outside curve is this one, x equals minus 3/2. So I need to write that in polar coordinates. How do I write x equals minus 3/2 in polar coordinates? Well, I remember that x is r cosine theta, so it's r cosine theta equals minus 3/2. And I divide by cosine theta and get r equals minus 3/2 secant theta. There it is. The top end point is minus 3/2 secant theta. So now you just have to do those two integrals. And they break up into pieces, right? Because the inside integral between constant endpoints, there's no theta left here after you integrate. You can just do the inside integral and the outside integral separately. What would be theta through and say this is integral from 0 to 2 pi over 3 d theta times integral from 0 to 3 r cubed dr. That's the first one. Then the second one, I can't pull d theta out of there. Why not? Because the endpoint evaluates at theta. So this inside integral is a function of theta. Not so easy. I'm just going to have to rewrite that as 2 pi over 3 to pi 0 to minus 3/2 secant theta r cubed dr d theta. And I'll finish it from there unless there's only the details. This integral, this becomes r to the 4th over 4 evaluated secant theta. Not too hard, but we'll avoid doing that. Save of doing some more problems today. Like say equals, etc. Any questions on setting that one up? Or if you really want to see this, we'll try. I'll get it started. All right. So that's that one. What else do we look at? By the way, there's not very many people are getting on Zoom. Actually, didn't look at an hour or something. If you get real stuck on these, once you get on it, Saturday afternoon from 2 to 3, I'll an extra hour, right? So Saturday, there gets to be a lot of people, maybe I'll continue past that. I'll just try and do some problems on the board by Zoom on your syllabus, the ones where the office address, not the address for the class. If there's a lot of questions, we'll eliminate it. No other questions, huh?
That's what I was going to say.
Okay. There's 3E. These spherical components divided a triple header. That's good. Got it down here on my paper. We want the triple integral of the square root of x squared plus y squared t squared. I'll have this on the board here. Over the solid W. That's a little different for that. A little different. X squared plus y squared plus z squared plus the variable gz. So find this triple integral over the solid. What kind of solid is this? X squared plus y squared plus z squared less than or equal to 2z. That's not one we've seen before. It doesn't look like a quadratic surface or sphere or anything. And actually, technically, it is a sphere. Can you see it? Tricky. You complete the square. X squared plus y squared plus z squared minus 2z equals 0. Put the parentheses suggestively. What do I have to do to make a perfect square in here? Make this a square. You don't actually have to do this part. I can add 1 in here. Take 1/2 of this coefficient, square it, add that over here to make a perfect square. Right? You take 1/2 of -2 squared is 1. That's what you need to add to make this a square. Then you have to add 1 to the other side to balance it. And so now I notice this is x squared plus y squared plus z minus 1 squared equals 1, or 1 squared, is a sphere of radius 1. Other things we learned by coming to class with this before. At the point 0, 0, 1. Right? So replace z by z minus 1 and sphere of the origin thing. We're trying to integrate over this solid. It's a sphere sitting on top of the origin of radius 1, center 0, 0, 1. That's up to 2. There it is, that's W. Now you don't actually have to draw that picture, I just think that gives you some insight. But how do I rewrite this in spherical coordinates? You can kind of see what spherical coordinates, because what is square root x squared plus y squared plus z squared in spherical coordinates? Yeah, that's rho. This is why there is memorization of those transformation laws. Otherwise, you might be all day trying to plug in x equals r cosine theta sine phi, y equals r sine theta sine phi, z equals rho, I should say, rho cosine phi, and squaring all those and using all your trig identities, it eventually reduces to rho. So the integrating this rho, that says we really sets this as a sphere, even though it's not at the origin. This is going to be easier in spherical coordinates. So this is rho, and what we have now is the triple integral of rho, and then dv becomes rho squared sine phi d rho d phi d theta. For our purposes in this class, it will always be this order for spherical coordinates, be rho d phi d theta, unlike x, y, and z that will switch around according to the symmetry of the problem. We're only interested in that one kind of region that we showed for spherical coordinates that has this order of integration. In this, theta and phi wind up going between constant endpoints for our purposes. Obviously, you can't do other cases, but it's tricky. Theta and phi, what is a constant theta and phi between which these goes? Can't speak. Well, what you can think is for a sphere, you can start in this direction and rotate all the way around. Theta goes all the way from 0 to 2 pi. Where does phi go? If you're thinking of sweeping this out with our little regions that we sketched before, adding up all the regions, phi starts going straight up at phi equals 0, and you can sweep out things inside the sphere until you get all the way down to phi equals pi over 2. And then at that point, you're just going out to a point. And so phi goes from 0 to pi over 2 here. You get points inside of the sphere. If you think of drawing this outward from an inside radius, rho equals 0, to an outside radius on the sphere, theta goes from 0 to 2 pi all the way around, but phi goes just down to the plane, which is pi over 2. That's the idea. You can think of this radial, this ray coming out from the origin and sweeping out from an inside surface to an outside surface, adding up all those little infinitesimal volumes along the way. Now, what does rho go between? It goes between the inside surface, which is this rho equals 0, just start at the origin, and it goes out to the sphere here. Oh, what's the sphere? I have to write rho as a function of theta and phi for the outside of the sphere. So I take the equation of the sphere and try and write rho as a function of theta and phi. So this is on the left side, x squared plus y squared plus z squared is rho squared, right? On the inside, 2z, I'm sorry, on the other side of the equation, 2z is 2 rho cosine phi. Remember, z is rho cosine phi from the coordinate transformation. Now you divide this through by rho, and you find out that rho equals 2 cosine phi is the equation of the sphere. So it's actually, in some ways, easier in spherical coordinates. If that's the equation of the sphere that we see, that's the outside surface, we just put 2 cosine phi at the surface. There's your triple integral setup. 0 to 2 pi, 0 to pi over 2, 0 to 2 cosine phi. Integrand rho times the volume element rho squared sine phi. Rho is 3 theta. Is that a mouthful? And talk too fast? Now you can do this one relatively easy, but you can't pull it all apart. You can pull the d theta through because there's no theta in here, right? So I can rewrite this as integral 0 to 2 pi d theta, which just evaluates the 2 pi. But I can't pull the other integrals apart because this integral is evaluated as a function of phi. So I'm just going to have to say times integral from 0 to pi over 2, integral from 0 to 2 cosine phi. We could pull the sine phi out of there. Let's put it here, sine phi. That comes out of the rho integrals treated as a constant. Rho cubed d rho d phi. Well, I would write it like that. Now you can do this double integral here and multiply by 2 pi over here.
How come we can't pull the dv out? Is it because for the rho integral we're using 2 cosine phi?
Yeah, because that's 2 cosine phi at the top. This integral is going to be a function of phi, and so you can't pull out of the phi integral. Yeah. So rho cubed integrates to rho to the 4th over 4. Plug in 0 and 2 cosine phi. Oh. Then I'll have to integrate when I'm all done with respect to phi. Okay. Let's see, that's 2 pi times integral from 0 to pi over 2 of 2 to the 4th is 16 over 4 is 4. So I got 4 cosine to the 4th of phi sine phi d phi. 4 doesn't sound very well, does it? 4. See how to do this one? Well, in this class, you'll get good at your calculus 1 and 2. How do I do this one? Yeah, let u equal, when you have an even power of a cosine times an odd, a power of cosine times power of sine, if at least one of the powers is odd, you can let u be the other one. So I'll let u equal cosine phi. And then du is minus sine phi dt. Right? Derivative phi dt. And so minus du can replace sine phi dt. So this is minus du, and this is u to the 4th. Oh, it's an easy integral. All right, I've got 8 pi integral from, we'll have to figure to do it in place, of minus u to the 4th du. Put my minus out back there. And then if when p is 0, u is cosine 0 is 1. And when phi is pi over 2, u is cosine pi over 2, which is 0. So now this from 1 to 0. Now let's see, this is minus 8 pi u to the 5th over 5. Evaluate it 1 to 0 and take the difference, gives you minus a 5th. You wind up at 8 pi over 5. Okay. So there's that. Hopefully this was on an answer sheet for you other time. Thank you for showing up today. see me on Zoom or see me after class, I feel whatever. I don't know if that's all good enough for you. Best wishes on Monday, don't come here for class on Monday, it's the exam, man.
You can't get wrong. You still want it. You don't have to divide by n when you do a that rate, right? Or do you still have to divide by n?
Give me just a second.